there's a gap in time that most of us never think about. A stretch of Earth's history so incomprehensibly massive that it dwarfs everything we know as human civilization. We're talking about the space between the world of dinosaurs and the world where humans walked upright. Between the reign of giant reptiles that ruled the planet for 160 million years and the emergence of our ancestors. If you zoom out and look at the entire timeline of life on Earth, this gap represents some of the most dramatic transformations the planet has ever undergone. Continents shifted, climates swung between extremes, entire ecosystems rose and fell, and somehow, from all that chaos, modern Earth was born. But here's what keeps paleontologists up at night. Most of this transformation is invisible to us. We have fossils from the dinosaur era. We have fossils showing early humans. But the period between them, the actual process of how one world became another, so much of it is missing. The fossil record goes quiet during the times we most desperately want to understand it. It's not that scientists haven't looked hard enough. They've been searching for over a century. They've excavated caves, explored remote deserts, dug through mountains of rock. But the Earth itself seems determined to keep its secrets locked away. Every year, paleontologists find new fossils that completely rewrite what we thought we knew about this period. A discovery that pushes back the origin of a group by 1 million years. And if you're using this video to fall asleep, perfect. That's exactly what it's for. So maybe hit subscribe and drop a comment telling me where you are and what time it is. I genuinely love checking those. It's wild seeing London at sunrise, New York at lunch, Los Angeles at midnight, all watching at the same time. A skull that suggests a species we thought went extinct actually survived longer. A footprint that proves humans were somewhere they weren't supposed to be. These discoveries are thrilling because they prove we're still learning, still uncovering pieces of a story that seemed settled. But they also highlight just how incomplete our understanding really is. For every fossil we find, there are thousands we'll never discover. For every piece of the puzzle we fit into place, there are millions of pieces that eroded to dust before anyone could study them. This is the story of the gaps, the lost chapters in Earth's history. The times when everything was changing and we're only now, billions of years later, trying to figure out what actually happened. The world shifted beneath our feet so completely that we can barely recognize it. And most of it happened in darkness, hidden from the fossil record, preserved only in fragments so incomplete they raise more questions than they answer. Between roughly 66 million years ago and the present day, the planet transformed from a world ruled by dinosaurs to a world where mammals dominate, where humans have evolved consciousness and built civilizations, where we're now trying to understand our own deep history. That transformation didn't happen gradually. It happened in jumps and starts and catastrophic collapses and explosive diversifications. And the story begins with an ending so final, so complete, that it has no parallel in modern experience. 66 million years ago, something happened that would divide Earth's history with a precision geologists can measure in centimeters of rock. An asteroid, roughly 6 miles across, was traveling through space at speeds so incomprehensible they make our fastest spacecraft look like they're standing still. And it hit Earth. Specifically, it hit what is now the Yucatan Peninsula in Mexico. The impact site, called Chicxulub, left a crater 93 miles wide and 12 miles deep. But saying it was a crater almost understates what happened. It wasn't just a hole in the ground. It was a wound in the planet itself. The energy released was equivalent to about 10 billion Hiroshima bombs. Let that sit with you for a moment. 10 billion. The explosion ejected roughly 25 trillion metric tons of debris into the atmosphere. Rock that had been solid ground seconds before was suddenly superheated vapor, molten droplets, pulverized dust, all of it thrown into the stratosphere at velocities so extreme that some material briefly escaped Earth's gravity before raining back down across the entire planet. The immediate aftermath was hell. Within hours, the sky everywhere on Earth was on fire. Those molten droplets falling back through the atmosphere created a global infrared pulse that essentially turned the planet's surface into a broiler. Forests that had stood for millions of years spontaneously combusted. Animals thousands of miles from the impact site suddenly found themselves in a world where the air itself was hot enough to kill. The dinosaurs that survived this initial firestorm probably thought the worst was over. They were wrong. Because when you throw 25 trillion metric tons of debris into the atmosphere, it doesn't just fall back down and disappear. The finest particles, microscopic dust suspended in the upper atmosphere, they blocked out the sun. Not partially, not like a cloudy day. We're talking about darkness so complete that photosynthesis became impossible across most of the planet. Scientists call this impact winter, but that name is misleading. It wasn't cold like winter. Temperatures in some regions dropped 50 degrees or more in the span of weeks. Earth went from a greenhouse world, warm and humid and teeming with life, to something closer to a frozen wasteland. The plants died first. Without sunlight, photosynthesis stops. Without photosynthesis, the entire food chain collapses. The fossil record shows this collapse with brutal clarity. Pollen samples from rock layers just above the impact show a catastrophic decline in plant diversity. Species that had dominated landscapes for millions of years simply vanish. In their place, massive spikes in fern spores. Ferns, those hardy survivors that can grow from underground systems even after surface vegetation is destroyed. When the plants died, the herbivores followed. The massive horned dinosaurs, the duck-billed hadrosaurs that roamed in herds thousands strong, the armored ankylosaurs. They all needed hundreds of pounds of vegetation daily just to survive. Within weeks of the impact, they would have been starving. Within months, dead. And when the herbivores died, the predators followed. The Tyrannosaurus rex, the raptors, all those magnificent killing machines that had ruled terrestrial ecosystems for over 160 million years. They starved too. Large predators can survive for weeks without food, so they probably lingered, hunting through forests of dead trees and fields of rotting corpses, finding less and less to eat until one by one they fell. 75% of all species on Earth went extinct, not gradually over thousands of generations, but in what geologists call an instant, which in geological terms means maybe a few thousand years, but probably much less. The boundary between the Cretaceous and Paleogene periods, between the age of dinosaurs and the age of mammals, you can literally put your finger on it. It's a thin layer of clay found in rock formations around the world, usually just a few centimeters thick, enriched with iridium, an element rare on Earth's surface but common in asteroids. Above that layer, dinosaur fossils. Below it, nothing but mammals and birds and survivors. That line represents the day the world ended, but it also represents the moment a new world began. Some things survived, not by being strong or fierce or specialized, but by being small, adaptable, and in many cases just plain lucky. Small mammals, most of them no bigger than rats, made it through. They could shelter underground. They could survive on insects and seeds and detritus. They didn't need vast territories or enormous food supplies. When the world was ending, being small and unspecialized turned out to be the greatest survival trait possible. Birds survived too, though just barely. Most bird lineages went extinct, probably because the ecological niches they depended on collapsed. But some made it through, mostly smaller ground-dwelling species that could eat seeds and insects. These survivors would eventually evolve into the 10,000 bird species alive today, but immediately after the impact, they were just handfuls of traumatized populations clinging to existence in a devastated world. Crocodiles and turtles survived, probably because they could go for long periods without food and tolerate extreme environmental conditions. Sharks and many fish species may die through because ocean ecosystems, while severely damaged, weren't quite as catastrophically disrupted as terrestrial ones. The immediate aftermath is where the story gets frustrating for science. We can see the world before the impact, thriving and diverse. We can see the impact layer itself, that thin band of iridium-rich clay marking the day everything changed. We can see what emerged millions of years later after the recovery. But the transition itself, those crucial years and decades when surviving species were adapting to a transformed world, when ecological relationships were being completely rearranged, when the stage was being set for everything that would follow, that period is obscure. The fossil record goes quiet right when things get most interesting. The world ends. The world begins again. And most of the details are lost to time. The world that emerged from the impact winter was fundamentally different from what came before. The climate was unstable, swinging between extremes as planetary systems tried to find new equilibrium. The forests that eventually grew back were different. Species adapted to different conditions. The animals that survived radiated into new forms, filling ecological niches left empty by the extinctions. And somewhere in that chaos, hidden in fragments we can barely see, the stage was being set for everything that would eventually lead to us. After the dinosaurs died, the dust settled and life found a way forward. The Paleocene epoch, the first 10 million years after the extinction event, was supposed to be straightforward. The slate had been wiped clean. Life could start over. Scientists should have been able to watch evolution happen in real time, see new species emerging from the ashes like a perfectly documented origin story. Except the Paleocene is when the fossil record decides to become frustratingly, maddeningly incomplete. Here's what we know happened in broad strokes. 75% of all species on Earth went extinct, but the small ones that could hide, that could eat almost anything, that could survive on scraps, those hung on. Mammals were among the survivors, but they weren't the mammals you're picturing. These were tiny creatures. Most were no bigger than a rat. Some were as small as shrews. They'd spent 160 million years living in the shadows of dinosaurs, evolving to be small, to be quiet, to be nocturnal, to be invisible. Then suddenly, the dinosaurs were gone. All of them. Every single dinosaur that wasn't a bird had vanished. The forests were burned. The landscape was devastated. But you were alive. And for the first time in your species' entire existence, nothing was hunting you. What would you do? You'd expand, you'd grow, you'd evolve. And that's exactly what happened. Within the first million years of the Paleocene, mammals began getting bigger. Not dramatically, not yet, but measurably. Species that had been mouse-sized started producing descendants that were rabbit-sized, then dog-sized. The evolutionary pressure that had kept them small for millions of years, that constant threat of being eaten, it was gone. But here's where the fossil record starts playing tricks on us. We should be able to track this transformation step by step. Watch these tiny survivors gradually becoming larger, diversifying, filling the empty ecological niches left by the dinosaurs. And we can sort of, but only in fragments, only in pieces so incomplete that scientists spend entire careers arguing about how they fit together. Take the issue of timing. How fast did this growth actually happen? Some fossil sites suggest rapid evolution, mammals doubling in size within a few 100,000 years. Other sites show much slower change, gradual increases over millions of years. Which is correct? We don't know because we don't have continuous fossil records from enough locations to be sure. We have snapshots, moments frozen in stone, separated by hundreds of thousands of years of missing time. It's like trying to watch a movie where 90% of the frames have been cut out. You see the opening scene, dinosaurs everywhere, cut to black. Next frame, they're gone, and small mammals are scurrying around the ruins. Cut to black. Next frame, those mammals are suddenly bigger, diversifying into different forms. Cut to black. The gaps aren't just annoying, they're hiding crucial evolutionary transitions, the moments when one thing became another thing, the exact sequence of changes that turned a tiny shrew-like mammal into something that could eventually become a horse, a whale, a bat, a primate. We know these transformations happened during the Paleocene, we just can't see them happening. Meanwhile, the planet itself was going through dramatic changes. The forests were coming back. Not the same forests that existed before the impact. Those were gone. Their seeds and saplings incinerated in the global firestorms. But new forests growing from whatever survivors had made it through. Ferns were among the first plants to reappear. They reproduced through spores that could survive extreme conditions. Within a few thousand years, vast fern prairies covered what had been barren landscapes. Then came the flowering plants, the angiosperms. They'd been relatively minor players before the extinction. After it, they exploded in diversity, becoming the dominant plant form across most of the planet. This created entirely new ecosystems that had never existed before. And mammals were evolving to exploit them in ways that would have been impossible under dinosaur rule. Some became specialized browsers, eating leaves and shoots. Others became fruit eaters, feeding on the abundant fruits produced by flowering plants. Still others became predators, hunting the other mammals that were multiplying in the dinosaur-free world. But we're missing most of the details. We know these adaptations happened because we find fossils of mammals that clearly had them. Teeth designed for grinding plants, limbs adapted for climbing trees, bodies built for running down prey. But the intermediate forms, the species that bridge the gap between the generalized survivors and these specialists, they're largely absent from the record. Fossilization requires very specific conditions. An animal dies, gets buried quickly before it decays or is scavenged, stays buried in sediment that eventually turns to stone, then somehow gets exposed millions of years later where paleontologists can find it. Each step in this process is unlikely. Most organisms that ever lived never fossilized. They died, decayed, and disappeared without leaving any trace. But the Paleocene seems to have been particularly bad for fossil preservation. The environmental chaos following the extinction created conditions that actually made fossilization less likely in many areas. Sea levels were fluctuating wildly. Climate zones were shifting. The stable depositional environments where fossils form best, river deltas, lake beds, shallow seas, they were constantly being disrupted. So we're left with tantalizingly incomplete evidence. We find a fossil here, another one 1,000 miles away, a third one separated from the first by 2 million years. And we try to connect them into a coherent story. But the connections require speculation, educated guesses based on anatomy, on evolutionary theory, on comparison with living animals. We can make reasonable inferences, but we can't be certain. Then, there are the creatures that show up in the Paleocene fossil record dominate for a while, and then just vanish entirely. No descendants, no clear explanation for why they went extinct. Consider the multituberculates. These were mammal-like creatures that had actually survived from the dinosaur era. They'd been around for over 100 million years, making them one of the most successful mammal groups in history. In the early Paleocene, they thrived. They grew larger, diversified, filled ecological niches from underground burrowers to tree-dwelling plant eaters. Fossil evidence suggests they were everywhere, possibly the most common mammals on Earth. Then they disappeared. Sometime during the Paleocene or early Eocene, the multituberculates went extinct. All of them. Every species. We don't know why. We don't know exactly when. We don't even have good fossils showing their decline. They're just there in older rock layers and absent from younger ones. 120 million years of evolutionary success wiped out during Earth's recovery period. And we missed it happening. The climate was also doing something extraordinary. For most of the Paleocene, temperatures were relatively cool by post-extinction standards. Not Ice Age cold, but cooler than the late Cretaceous had been. The planet was recovering, but slowly. Ecosystems were rebuilding piece by piece. Then, right at the end of the Paleocene, about 56 million years ago, something dramatic happened. Global temperatures suddenly spiked. Not over millions of years, over thousands of years, maybe even faster. This event, called the Paleocene-Eocene thermal maximum, saw average global temperatures rise by 5 to 8 degrees Celsius in a geological instant. The effects were catastrophic. Ocean chemistry changed, becoming more acidic. Deep-sea creatures experienced mass extinctions. On land, entire forests migrated, poleward, following their preferred temperature ranges. Tropical conditions extended far into what are now temperate zones. And mammals, those survivors who'd been steadily diversifying for 10 million years, suddenly faced a new crisis. We should be able to see how they responded in detail. Watch them adapt, migrate, evolve new heat tolerance mechanisms. Track the species that made it through versus those that didn't. And we can But the fossil record from this thermal maximum is once again frustratingly patchy. We have some excellent sites that preserve snapshots of the event, but vast regions of the planet have no fossil record from this period at all. The Paleocene is Earth's recovery period, but it's also one of paleontology's most beautiful mysteries, a time when everything changed and we missed watching most of it happen. 56 to 34 million years ago, Earth underwent a transformation so complete that if you could somehow visit that world, you might not even recognize the planet you were standing on. The name for this period is the Eocene, which means dawn of the recent. But there was nothing remotely recent about the conditions on Earth during this time. This was the last period when our planet was a true hothouse world. No ice anywhere, not at the poles, not on mountains, nowhere. The entire planet was a greenhouse. Picture yourself standing in what will one day be Alaska. But instead of tundra and permafrost, you're surrounded by palm trees. Actual palm trees swaying in the warm Arctic breeze. The temperature is a comfortable 70 degrees Fahrenheit in the Arctic all year round. Because during the Eocene, there were no seasons as we know them. The global climate was so warm that temperature differences between the equator and the poles were minimal, maybe 20 degrees instead of the 100-degree difference we see today. Crocodiles swam in rivers where London now stands. Alligators basked on riverbanks in Wyoming. Lemur-like primates climbed through rainforests that covered what is now the American Midwest. The Arctic Ocean was warm enough to swim in, sometimes reaching temperatures of 70 to 75 degrees Fahrenheit at the surface. For comparison, That's warmer than modern California beaches. But here's where it gets really strange. We don't fully understand why the Eocene was so warm. Yes, atmospheric carbon dioxide levels were higher, maybe 1,000 to 2,000 parts per million compared to today's 420. But the climate models don't fully add up. Even with elevated CO2, the temperatures at the poles were way higher than our models predict they should have been. There's something missing from our understanding, some feedback mechanism in Earth's climate system that we haven't figured out yet. A gap in our knowledge about how the planet regulates heat when it gets this warm. And this wasn't a short period. The Eocene lasted 22 million years. For context, that's longer than the entire time between the asteroid impact that killed the dinosaurs and the beginning of the Eocene. 22 million years of unbroken tropical conditions worldwide. 22 million years for life to adapt to this hothouse world and evolve into forms we can barely recognize. The mammals that emerged during the Eocene were like nothing that exists today. Sure, there were early versions of groups we recognize. Primitive horses the size of dogs. Early whales that still had legs and walked on land. Ancient primates experimenting with life in the trees. But there were also entirely new groups of mammals that have no modern descendants. Lineages that thrived for millions of years and then vanished completely, leaving behind only fragments of fossils and massive questions about what they were and how they lived. Take the creodonts. These were the apex predators of the early Eocene, filling the ecological roles that big cats and wolves fill today. But they weren't related to modern carnivores at all. They were a completely separate evolutionary experiment in being a meat-eater. Some were massive, bigger than modern lions. Others were small and weasel-like. They dominated for millions of years, and then disappeared around 35 million years ago, replaced by true carnivores, the ancestors of modern cats and dogs and bears. We don't know why the creodonts died out. We don't know why true carnivores were more successful. We just know that one group replaced the other, and millions of years of evolutionary history went extinct without leaving clear explanations in the fossil record. Or consider the Brontotherians. Imagine a rhinoceros but stranger, much stranger. These massive herbivores looked like someone took a rhino and gave it elaborate Y-shaped horns, then scaled it up until some species were 8 feet tall at the shoulder and weighed 4 tons. They were everywhere during the Middle Eocene, dominating North American and Asian ecosystems. Then around 34 million years ago, they all disappeared within what seems like geological seconds. The entire family, dozens of species gone. The fossil record shows them thriving 1 million years, then absent the next. What happened? Climate change, disease, competition with other herbivores. Nobody knows. The Eocene fossil record should have been incredible. Warm, wet conditions mean lush vegetation, abundant life, lots of animals dying and getting buried in sediments. But instead, the Eocene fossil record is full of holes, massive gaps where we should have thousands of specimens but instead have handfuls. Critical transitional periods where we'd love to see how species evolved but find almost nothing. Why? Partly it's geology working against us. The Eocene was a time of intense geological activity. Continents were moving faster than at almost any other period in Earth's history. India was slamming into Asia, creating the Himalayas, and in the process destroying or burying countless fossil beds. The Atlantic Ocean was widening, pulling North America and Europe apart, subducting seafloor and taking fossil-bearing sediments down into the mantle where they'd be melted and destroyed. The Rocky Mountains were being uplifted, tilting and fracturing rock layers, mixing up the geological record until figuring out what happened when became nearly impossible. But it's also the environment itself. Tropical rainforests, which covered huge portions of Eocene Earth, are terrible for fossil preservation. The heat and moisture cause bodies to decompose rapidly. The acidic soils dissolve bones. The constant growth and decay of vegetation churns up the ground, destroying burial sites. Modern tropical rainforests are among the most biodiverse places on Earth, but they produce almost no fossils. 34 million years ago, something dramatic happened. The hothouse world ended, not gradually, but relatively suddenly in geological terms. Within less than 1 million years, global temperatures dropped by 15 degrees Fahrenheit. Ice sheets formed in Antarctica for the first time in over 20 million years. The tropical forests that had covered huge portions of the planet retreated toward the equator, and a massive extinction event swept across the world. We know this happened. The geological and fossil evidence is clear, but we don't fully understand why. The leading theory involves changes in ocean currents. As continents continue drifting, the Drake Passage between South America and Antarctica finally opened wide enough to allow the Antarctic circumpolar current to form. This current isolated Antarctica, preventing warm tropical waters from reaching it and allowing it to freeze. The formation of Antarctic ice sheets then created a feedback loop, reflecting more sunlight, cooling the planet further, causing even more ice to form. But here's the problem. The timing doesn't quite work. Some evidence suggests the cooling began before the Drake Passage fully opened. Other evidence shows periods of warming in the middle of the overall cooling trend. The transition wasn't smooth. It was chaotic, stuttering, full of false starts and reversals. The Eocene stands as a massive gap in our understanding of how Earth's climate and ecosystems function under extreme conditions. 22 million years of hothouse conditions that produced life forms we can barely imagine and then wipe them away in a geological instant. A period when palm trees grew at the poles and crocodiles swam in Arctic rivers. When bizarre mammal lineages rose and fell without leaving clear explanations for their existence. And perhaps most importantly, a period that contained the evolutionary origins of our own lineage. Somewhere in those Eocene rainforests, among those fragmentary fossils and massive gaps in the record, our ancestors were evolving. From 34 to 5 million years ago, nearly 30 million years of Earth history that should be absolutely packed with answers to our biggest evolutionary questions. Instead, the Oligocene and Miocene epochs are like someone took the most important chapters of Earth's autobiography and fed them through a shredder. Here's what we know was happening during this time. The planet was cooling steadily, dramatically, transforming from the hot, humid world of the Eocene into something that would eventually become recognizable as the modern Earth. Antarctica, which had been forested and relatively warm just a few million years earlier, froze solid around 34 million years ago. Within a few 100,000 years, it went from a temperate continent with trees and rivers to a frozen wasteland covered in ice sheets miles thick. That transformation should have been documented in thousands of fossil sites across the globe. We should have layer upon layer of sediment showing the gradual shift from one climate to another, from one ecosystem to another. Instead, we have gaps. Massive, inexplicable gaps where entire ecosystems simply vanish from the fossil record with no clear transition, no connecting evidence, nothing. The cooling didn't stop with Antarctica. Over the next 30 million years, global temperatures continued their downward slide. The hot, jungle-covered world that had dominated Earth for hundreds of millions of years was dying, and something new was emerging. Grasslands. Now, grasslands might not sound particularly exciting, but this was one of the most revolutionary ecological transitions in Earth's history. For most of the age of mammals, The planet had been dominated by forests, dense, tangled vertical ecosystems, where success meant being able to climb, swing, hide in the canopy. Then, relatively suddenly in geological terms, huge swaths of those forests disappeared. They were replaced by open spaces, endless plains of grass stretching from horizon to horizon. This should be one of the best documented transitions in Earth's history. The shift from forest to grassland would have affected every animal on the planet. New species would have emerged to exploit the open spaces. Old species would have gone extinct or adapted. The fossil record should show us this transformation in exquisite detail, layer by layer, species by species. Except it doesn't. What we have instead are snapshots, brief windows into this 30 million year period, separated by enormous gaps. We have forest ecosystems from the early Oligocene, then millions of years of nothing. Then suddenly, in the late Miocene, we have vast grasslands with completely different animal communities. The transition between them, the actual process of transformation, is largely missing. And nowhere is this more frustrating than when it comes to our own ancestors. Because somewhere during the Oligocene and Miocene, something incredibly important happened. Apes evolved. Not just any apes, but the lineage that would eventually lead to humans. This should be the most intensely studied period in all of paleontology. This is when our family tree started branching. This is when the characteristics that make us human first began to emerge. Instead, what we have is what scientists politely call a substantial gap in the fossil record. Around 25 million years ago during the Oligocene, primitive apes started appearing in Africa. These weren't like modern apes. They were smaller, more monkey-like, still spending most of their time in trees. But they had certain characteristics, dental patterns, limb proportions, skull shapes that mark them as apes rather than monkeys. They were our ancestors, the beginning of our line. Then the fossil record goes dark. For millions of years, we have almost nothing. A tooth here, a jaw fragment there, but no complete skeletons, no clear evolutionary sequences, no way to track how these primitive apes were changing and adapting. When the fossil record picks up again in the middle, around 15 million years ago, everything has changed. Now we have multiple ape species spread across Africa, Europe, and Asia. Some are small and gracile, others are massive, weighing hundreds of pounds. Some are clearly adapted for life in trees. Others show early signs of terrestrial adaptation. The diversity is stunning, and the evolutionary relationships between them are almost impossible to untangle because we're missing the connecting fossils that would tell us how they're related. These are called ghost lineages, evolutionary lines that must have existed, that had to have existed based on genetic and anatomical evidence, but which left almost no fossil trace. The mathematics of evolution tells us they were there. DNA analysis of modern apes confirms they existed, but the rocks are silent. For roughly 10 million years during a critical period when apes were diversifying and spreading across 3 continents, we have maybe a few dozen partial specimens total. To put that in perspective, we have better fossil documentation of dinosaurs from 100 million years ago than we do of our own ancestors from just 20 million years ago. Why? What happened to all those fossils? Part of the answer is geology. The Oligocene and Miocene were periods of intense geological activity. Mountain ranges were forming. Africa was drifting north, creating new geological complexes. All this geological chaos was fantastic for creating dramatic landscapes, but terrible for preserving fossils. Fossilization requires very specific conditions. You need the right kind of sediment, the right water chemistry, right rate of burial, and you need all of that to remain undisturbed for millions of years. But during the Oligocene and Miocene, vast areas of Africa and Eurasia were being uplifted, eroded, folded, and fractured. Sediments that might have contained fossils were being destroyed as fast as they formed. The climate chaos made things worse. This was a period of dramatic global cooling. But that cooling wasn't smooth and steady. It was punctuated by sudden climate shifts, periods of rapid change that could transform entire ecosystems in just a few thousand years. These rapid transitions were devastating for fossil formation. Fossils form best in stable environments, lake bottoms where sediment accumulates year after year undisturbed, river deltas where flooding regularly buries organisms in mud. But when the climate is changing rapidly, these stable environments disappear. Lakes dry up, rivers change course, forests die and are replaced by grasslands, which don't preserve fossils nearly as well. During the Oligocene and Miocene, Earth was experiencing some of the most dramatic climate swings in mammalian history. These fluctuations created an ever-changing mosaic of environments, none of them stable enough to preserve good fossil records. Horses, for instance. We know they evolved from small multi-toed forest dwellers into large single-toed plains runners during the Miocene. This transformation required massive changes to their anatomy, their digestive system, their behavior, everything. It should be one of the best documented evolutionary transitions we have. And in North America it is. The fossil record of horse evolution in North America is actually quite good. We can track the changes step by step. But in Eurasia and Africa, where horses also evolved and spread during the same period, the record is fragmentary at best. Whole branches of the horse family tree appear and disappear with no clear ancestry, no obvious descendants. They're evolutionary orphans, species that existed but which we can't connect to anything that came before or after. The same pattern repeats across dozens of mammal groups. Modern elephants evolved during the Miocene from smaller ancestors. But the transitional forms, the species that link primitive proboscideans to modern elephants, are mostly missing. We have the endpoints, but not the journey between them. Modern big cats evolved during this period. Lions, tigers, leopards all emerge from a common ancestor that lived sometime in the Oligocene or early Miocene. But we have almost no fossils showing how this diversification happened. The earliest clear lion fossil is only about 3.5 million years old. But genetic analysis tells us lions split from other big cats at least 10 million years ago. Where are those 6 million years of lion evolution? Gone, erased, lost to time. Even modern primates, our closest relatives, show the same frustrating pattern. Gorillas, chimpanzees, orangutans, all these species have ancient origins stretching back into the Miocene, but their fossil records are essentially non-existent. We have more fossil evidence of extinct ape species that aren't closely related to anything alive today than we do of the direct ancestors of our closest living relatives. This creates a bizarre situation. We know more about evolutionary dead ends than we do about successful lineages. The species that went extinct often left better fossils than the ones that survived. It's like having a history book where all the chapters about important civilizations have been torn out, but the footnotes about minor kingdoms that collapsed are still intact. And grasslands make everything worse because grasslands are terrible for preserving fossils compared to forests and wetlands. In a forest, when an animal dies, it often falls into water or gets buried in soft, organic-rich soil. Perfect conditions for fossilization. But on a grassland, dead animals are exposed to scavengers, weather, and bacterial decay. Within weeks, most carcasses are scattered and destroyed. Only under very specific circumstances, like being buried by a flash flood or falling into a sinkhole, Do they have any chance of fossilization? So as forests gave way to grasslands during the Miocene, the probability of fossil preservation dropped dramatically. And this happened exactly when apes were undergoing their most important evolutionary developments. The timing couldn't have been worse for paleontologists, but here's what really haunts researchers who study this period. It's not just that we're missing fossils, it's that we're probably missing entire species, entire evolutionary experiments that rose and fell, leaving no trace whatsoever. Genetic analysis of modern apes suggests there should have been dozens of ape species living during the Miocene. Different lineages branching and evolving, competing for resources, adapting to new environments. The genetic diversity we see today could only have come from a much larger ancestral population with far more species than we've found fossils of. So where are they? How many species evolved and went extinct during those 30 million years without leaving a single fossil? How many potential ancestors to humans lived and died without us ever knowing they existed? The ghost lineages haunt us precisely because we know they must have been real, but we can't see them, can't study them, can't even properly acknowledge their existence except as gaps in our understanding. Those gaps have real consequences for understanding human evolution. Because somewhere in those missing millions of years, something happened that set our lineage on a unique path. Somewhere between 25 and 5 million years ago, the ancestors of humans diverged from the ancestors of other apes. They developed characteristics that would eventually lead to bipedalism, tool use, enlarged brains, all the features that make us human. But we don't know when. We don't know how. We don't know what environmental pressures drove these changes, or what intermediate forms connected primitive apes to the first recognizable hominins. The Oligocene and Miocene should answer these questions. Instead, they mock us with absence. What we're left with is speculation built on fragments. We can guess that climate change played a role, that the spread of grasslands created new selective pressures, that competition between ape species drove innovation and adaptation. But we're guessing, building elaborate theories on foundations of sand, hoping that someday, somewhere, someone will find the fossils that fill in the gaps. Until then, these epochs remain the lost middle chapters, the crucial period between the ancient world of forests and the modern world of grasslands. The time when our ancestors transformed from generic apes into something unique. The 30 million years that should explain everything, but instead explain almost nothing. And yet by the time the Miocene gave way to the Pliocene 5 million years ago, something remarkable had happened. The apes had undergone a revolution, and somewhere among them, walking on two legs through the African grasslands, were the first creatures that looked almost but not quite like us. The Pliocene epoch, 5 to 2.6 million years ago, was supposed to be different. This was the time when our ancestors stopped being apes and started becoming human. We know it happened. We can see the before and after. But the actual transition, the moment when everything changed, it's mostly missing. And here's what makes this particularly maddening. We're not talking about some obscure group of ancient reptiles that lived in remote corners of the earth millions of years before anything resembling humans existed. We're talking about our direct ancestors, the individuals who developed upright walking, tool use, enlarged brains, all the features that make us human. They lived relatively recently in geological terms. They left evidence of their existence. But we have so few fossils that you could fit nearly all the significant Pliocene hominin specimens in a single room. Think about that. The entire physical record of humanity's emergence as a distinct lineage could be stored in your living room. Every crucial fossil that documents our transformation from tree-dwelling apes to ground-walking tool users, a handful of partial skeletons, scattered bones, fragments of skulls. That's it. That's all we have to explain the most important evolutionary transition in our lineage. And it's not because nobody's looking. Paleoanthropologists have been searching East Africa for over a century. They've examined thousands of fossil sites, sifted through millions of tons of sediment, dedicated entire careers to finding the missing pieces of our origins. They found some remarkable things, sure, but the gaps between those discoveries are enormous. We have Lucy, the famous Australopithecus afarensis skeleton discovered in Ethiopia in 1974. She's about 3.2 million years old, and she's one of the most complete early hominin fossils ever found. About 40% of her skeleton survived, which in paleoanthropology terms makes her practically intact. She tells us that by 3.2 million years ago, our ancestors were definitely walking upright. Had brains still similar in size to apes, but bodies that were starting to look human. She's a snapshot, a single moment frozen in time. But here's the problem. Lucy represents one individual who lived for maybe 20 or 30 years, 3.2 million years ago. We have very little from the 200,000 years before her, and not much more from the 200,000 years after. She's standing alone in a vast temporal emptiness, a single data point trying to represent hundreds of thousands of years of evolution. The other Australopithecus fossils we've found don't fill in the picture much better. They're scattered across time like breadcrumbs, each one separated from the next by 100,000, 200,000, sometimes 500,000 years. Imagine trying to understand a person's entire life story, but you only have photographs from when they were 2 years old, then 12, then 47, then 83. You could see they changed. You could guess at what happened in between, but you'd be missing almost everything that made them who they are. That's what we're dealing with in the Pliocene. We can see that something incredible happened. Apes became humans, but we're missing the actual process. The gaps aren't random. They're systematic, concentrated in exactly the times and places where we most need evidence. Between 4 and 5 million years ago, right when the earliest hominins should have been diverging from other apes, we have almost nothing. A few teeth from Kenya, some skull fragments from Chad, these tantalizing hints that something was happening. But not enough to say what. Then there's the gap between 2 and 3 million years ago, right when the genus Homo, our genus, was emerging from Australopithecine ancestors. We have a handful of fossils that might be transitional forms, but they're so fragmentary and scattered that experts can't even agree on how many species they represent. Some researchers think there were 3 or 4 distinct human species coexisting during this period. Others argue for 6 or 7. A few think there might have been a dozen or more lineages, most of which went extinct without leaving any fossil record at all. They're arguing about ghost species, entire branches of the human family tree that we know must have existed based on genetic and geological evidence, but which have left no physical trace. And here's what makes the Pliocene gap so particularly frustrating. We know exactly where to look. The fossil evidence we do have points clearly to East Africa as the cradle of humanity. The Rift Valley region stretching from Ethiopia through Kenya and Tanzania. That's where the hominin revolution happened. We know the location. We've identified the right geological formations. We found enough fossils to prove our ancestors were there. But the preservation is terrible. The conditions that made East Africa perfect for human evolution made it terrible for fossilization. Because here's the thing about fossils, they don't just happen. Fossilization requires very specific conditions. You need the right type of sediment, usually fine-grained material. that can quickly bury and protect organic remains. You need the right water chemistry, minerals that can infiltrate and replace bone before it decays. You need geological stability. The fossil site has to remain undisturbed for millions of years, not get eroded away or destroyed by volcanic activity or tectonic movement. And you need luck. Even under perfect conditions, fossilization is incredibly rare. Most organisms that die are consumed by scavengers, decomposed by bacteria, scattered by weather, and disappear without a trace. Now take all those requirements and try to apply them to Pliocene East Africa. It doesn't work. The Rift Valley was, and still is, one of the most geologically active places on Earth. Volcanoes erupting regularly, earthquakes constantly shifting the landscape, rivers changing course every few thousand years. The environment was perfect for evolution, changing rapidly enough to create strong selection pressures, driving our ancestors to adapt or die. But that same dynamism was terrible for preservation. Volcanic eruptions would bury potential fossil sites under meters of ash. Tectonic activity would uplift sedimentary layers, exposing them to erosion. Rivers would cut through ancient deposits, washing away millions of years of history. Most of the time, our ancestors were living in woodlands and grasslands, not near lakes or river deltas where fossilization is most likely. They were mobile, following resources across the landscape, not staying in one place long enough to create concentrated bone deposits. When they died, their bodies were probably quickly consumed by the rich scavenger community that existed in Pliocene Africa: hyenas, vultures, insects. Within days or weeks, nothing would remain but scattered bone fragments, and those fragments would be exposed to weathering, cracking, disintegrating, turning to dust long before they had any chance of being buried and preserved. The few fossils we found are the exceptions. The 1 in a million instances where everything went right. An individual happened to die near a lake or stream. Sediments happened to bury them quickly. Mineral-rich water happened to infiltrate the bones. The deposit happened to remain undisturbed for millions of years. And modern erosion happened to expose the fossil at just the right time for a paleoanthropologist to find it before weather destroyed it. Every hominin fossil from the Pliocene represents a winning lottery ticket. Millions of our ancestors lived and died during this period. But we found maybe a few hundred individuals, and most of those are represented by just a single bone or tooth. This creates enormous problems for understanding human evolution. We're trying to reconstruct the story of how we became human, but we're working with a tiny, biased, fragmentary sample of the actual population. It's like trying to understand American history, but the only evidence you have is 3 photographs from the Civil War, a diary entry from 1923, and a newspaper from 1967. You could see that things changed. You could guess at the major events, but you'd be missing almost everything. The gaps create space for massive uncertainty and debate. Between the fossils we have found, there's room for almost any evolutionary scenario. Did early hominins evolve gradually, slowly accumulating human features over millions of years? Or did they evolve in rapid bursts, long periods of stasis interrupted by quick transformations? We can't tell because we don't have enough data points. How many species of early humans coexisted during any given period? We don't know. The fossils we have might represent distinct species, or they might just show normal variation within a single species. Did our ancestors develop upright walking first and then increase brain size? Or did both happen together? The fossil record can support either interpretation. Now we're in the Pleistocene epoch, 2.6 million to 11,700 years ago. The Ice Ages, the time when humans evolved from primitive hominids into behaviorally modern people, the period when we spread across the entire planet. developed language, created art, invented tools sophisticated enough to hunt woolly mammoths and saber-toothed cats. This is recent. This is practically yesterday in geological terms. This is so recent that some Pleistocene animals are still alive. Elephants, rhinoceroses, lions. These are Pleistocene species that survived into the modern world. And yet we have absolutely massive gaps in our understanding of this period. Gaps that make no sense. Gaps that seem to violate everything we think we know about how archaeology and paleontology work. Here's the paradox that keeps paleontologists awake at night. We have better, more complete fossils of dinosaurs that lived 66 million years ago than we do of human ancestors who lived 100,000 years ago. Think about that. Really think about it. A Tyrannosaurus rex that died 66 million years ago. We can find nearly complete skeletons. We can study their bone structure, analyze their growth patterns, determine what they ate and how they moved. Museums around the world display T-Rex skeletons that are 70, 80, sometimes 90% complete. But a Neanderthal who died 40,000 years ago, we're lucky if we find a jawbone and a few teeth. Most Neanderthal specimens are so fragmentary that we're reconstructing entire populations from partial skulls and scattered limb bones. The Denisovans, an entire human species that lived across Asia until maybe 30,000 years ago. We found exactly one finger bone, a handful of teeth, and a piece of skull. That's it. That's everything we have from an entire species that was spread across millions of square miles and survived for hundreds of thousands of years. We've identified these people, mapped their genome, figured out they interbred with modern humans and Neanderthals, determined they adapted to high altitudes and developed maritime technologies. All from a finger bone found in a Siberian cave in 2008. It's absurd. It's like trying to reconstruct the entire history of the Roman Empire from a single coin and 3 bricks. And it gets worse because the Denisovans aren't alone. In 2004, scientists discovered Homo floresiensis, the so-called hobbits, on an Indonesian island, a completely unknown human species that survived until maybe 50,000 years ago. We had no idea they existed. None. Then suddenly we're digging up skeletons of 3-foot-tall humans with brains the size of chimpanzees who somehow figured out how to make sophisticated stone tools and hunt dwarf elephants. In 2015, we found Homo naledi in South Africa, another completely unknown human species. Thousands of bones in a single cave system, and we still can't figure out how old they are. Initial estimates put them at 2 million years old based on their anatomy, but dating of the fossils suggested they might have survived until 230,000 years ago. That would mean they were alive at the same time as early modern humans. How do you lose an entire human species? How do you lose multiple human species? These aren't microscopic organisms. These are large mammals with complex social structures who made tools, used fire, buried their dead. They left footprints. They created archaeological sites. They should be everywhere in the fossil record, but they're not. They're ghosts, shadows. We know they existed only because of a handful of chance discoveries in caves and volcanic ash deposits where conditions happen to be perfect for preservation. The conventional explanation is that the Pleistocene ice ages destroyed most of the evidence, and that's partially true. For 2.6 million years, massive ice sheets advanced and retreated across the northern hemisphere. At the peak of glaciation, ice up to 2 miles thick covered Canada, most of northern Europe, and vast stretches of northern Asia. That ice was like a continental bulldozer. It scraped away topsoil, crushed rock into gravel, obliterated everything in its path. When the glaciers finally retreated about 11,700 years ago, they left behind landscapes completely transformed. Valleys had been carved into fjords, mountains had been ground down, river courses had been completely rerouted. Any archaeological sites, any human habitation areas, any evidence of populations living in those regions was simply erased. Ground into dust and scattered meltwater floods that were bigger than anything in recorded history. So okay, that explains the gaps in the glaciated zones. But humans didn't just live under the ice. They lived in Africa, Asia, Australia, South America, regions that were never glaciated. Where's all their evidence? This is where the paradox gets even stranger. Because we're missing more than just fossils. We're missing archaeological sites. We're missing the places where people actually lived. Archaeological sites older than 50,000 years are extraordinarily rare. Not just uncommon. Rare to the point of being almost non-existent. We can count on our fingers the number of well-preserved archaeological sites from before 50,000 years ago. And most of those are caves. Places where unusual conditions allowed preservation. Open-air sites, campsites, hunting grounds, processing areas. The places where people actually spent most of their time. Almost nothing survives. But here's what really doesn't make sense. During the Pleistocene, there were millions of humans living across multiple continents for hundreds of thousands of years. They were making tools constantly. Stone tools, bone tools, wooden implements. They were processing food, creating hearths, building shelters. They should have left behind billions of artifacts. Even if 99% of those artifacts were destroyed by natural processes, we should still be finding them everywhere. Every eroding riverbank should be full of stone tools. Every cave should contain multiple occupation layers. The archaeological record should be dense and continuous. But it's not. It's sparse, fragmentary, full of massive temporal gaps where we have essentially nothing. And then there's the megafauna extinction. Between about 50,000 and 10,000 years ago, the majority of large mammal species on Earth went extinct. Woolly mammoths, mastodons, saber-toothed cats, giant ground sloths, cave bears, woolly rhinoceroses. In North America alone, we lost 34 genera of large mammals. In South America, 50 genera disappeared. Australia lost nearly all its megafauna. This is one of the most dramatic extinction events in Earth's history. And it happened right when humans were spreading across the globe. The correlation is obvious. We showed up. The megafauna disappeared. But here's the problem. We have almost no direct evidence of humans hunting these animals to extinction. Yes, we have a handful of kill sites. Yes, we have mammoth bones with spear points embedded in them. But we're talking about dozens of sites documenting the extinction of hundreds of species across multiple continents. The math doesn't work. If humans hunted mammoths, mastodons, and giant sloths to extinction, there should be thousands of kill sites, massive bone beds full of butchered remains, processing areas where people systematically harvested these animals generation after generation. Where are they? Where's all the evidence of this supposed extinction-level hunting pressure? Fossilization is unbelievably, spectacularly, almost impossibly rare. Think about every animal that dies today. Every bird that falls from the sky. Every deer that collapses in the forest. Every fish that stops swimming and sinks to the ocean floor. How many of them will become fossils? How many will still exist as recognizable remains 10 million years from now, let alone 50 million or 200 million? The answer is almost none, effectively zero. Because here's the thing about fossilization. It requires a perfect storm of conditions that almost never happens. First, the organism has to die in exactly the right place. Not on a hillside where scavengers will tear it apart and scatter the bones. Not in a stream where the current will break the skeleton into pieces. Not in the open where sun and weather will bleach and crumble everything into dust. It needs to die somewhere it can be buried quickly before decomposition and scavengers do their work. A riverbed where sediment will cover it during the next flood. A mudslide that entombs it instantly. A peat bog where the chemistry of the water prevents decay. Already we're down to maybe 1 in a million organisms that even gets to this stage. But that's just the beginning. Once buried, the organism needs to stay buried for millions of years undisturbed, while chemical processes slowly replace organic material with minerals, turning bone into stone. This process, called permineralization, requires specific groundwater chemistry, specific mineral content, specific pH levels. Get any of it wrong and the bone just dissolves away, leaving nothing behind. Even when everything goes right, the fossilization process is selective. Hard parts, bones and shells and teeth, those might survive. But soft tissue, skin, muscles, organs, feathers, gone. Completely erased from the geological record, except in the rarest of circumstances. This means we're essentially working with skeletal blueprints, trying to reconstruct entire living organisms from their bones alone. And we've only just started listing the problems. Let's say an organism beats all those odds. It dies in the right place, gets buried quickly, stays buried, and successfully fossilizes. Now, it needs to survive millions of years of geological violence because the Earth doesn't just sit still. The Earth is constantly destroying its own history. Plate tectonics is the great eraser of the fossil record. Every year, tectonic plates drift a few centimeters. Doesn't sound like much, but over millions of years, those plates move thousands of miles. They collide, creating mountain ranges that thrust ancient seafloors into the sky. They split apart, opening ocean basins where dry land used to be. And most destructively, they subduct. One plate slides beneath another, dragging down into the mantle where temperatures and pressures turn everything to magma. Gone. Melted back into molten rock. Entire continents worth of fossils, entire epochs of evolutionary history, just recycled back into the Earth's interior. The Pacific Ocean floor, for example, is almost entirely less than 200 million years old. Everything older has been subducted. Millions of years of ocean life, entire marine ecosystems from the Paleozoic and early Mesozoic eras, destroyed by geological recycling. We'll never know what lived there, never see fossils of those organisms. The evidence has literally melted away, but subduction isn't the only destroyer. Mountain building crumples rock layers like paper, fracturing fossils into unrecognizable fragments. Volcanic eruptions bury fossil beds under meters of igneous rock or heat them until organic remains are burned away completely. Metamorphism, the transformation of rock under heat and pressure, obliterates fossils by recrystallizing the very stone they're preserved in. There are vast regions where Paleocene and Eocene rocks exist, but any fossils they once contained have been destroyed by metamorphic transformation. The rocks are still there. The history is gone. Then there's erosion, the slow-motion destruction of everything. Mountains rise and immediately wind and water begin tearing them down. Every rainstorm carries away a little more sediment. Every freeze-thaw cycle cracks rocks apart. Every river carves deeper into ancient layers. Over millions of years, erosion can remove thousands of feet of rock, and with it, every fossil that rock contained. Entire geological formations representing millions of years of time, worn away to nothing and washed into the ocean. The fossils we do find are the result of this impossible process, working in reverse. Erosion has to remove just enough rock to expose the fossil layer, but not so much that it destroys the fossils themselves. Then, by pure chance, a paleontologist has to happen to be in that exact spot during the brief geological moment, maybe a few hundred years, when the fossils are exposed before erosion finishes destroying them. The odds are astronomical. Most fossils that survive fossilization and millions of years of geological violence never get discovered. They're buried under cities, highways, farmland. They're underwater. They're in remote mountains or deep jungles or vast deserts where no paleontologist will ever look. They're exposed during a storm and eroded away before anyone sees them. They're found by people who don't recognize them as fossils and just leave them there. Professional paleontologists estimate that we've discovered less than 1% of all fossils that ever existed. 1%. And remember, only a tiny fraction of organisms that ever lived became fossilized in the first place. We're looking at multiple layers of improbability. 1 in a million organisms fossilize. 1 in 100 fossilized organisms survive to the present. 1 in 100 surviving fossils ever get discovered. Do the math. For every fossil in a museum, there might be 1 billion organisms that lived and died without leaving any permanent trace. This preservation bias gets even more complicated when you consider environment. Some environments are fantastic for fossil preservation. River deltas, lake beds, coastal lagoons, places where sediment accumulates steadily and buries things quickly. These environments are overrepresented in the fossil record. We have detailed knowledge of ancient swamps and riverbanks because those are the conditions that preserve fossils best. But mountains, forests, grasslands, these environments rarely preserve anything. An animal dies on a hillside and the body's exposed to scavengers, weather, and gravity. Bones scatter down slopes, break apart, and disappear. 1 million years later, erosion might remove that entire hillside, and there's nothing left to find. This means entire ecosystems are nearly invisible to paleontology. We know far more about ancient coastal wetlands than we do about ancient mountains. Not because mountains were less important, but because mountains don't preserve fossils well. And soft-bodied organisms might as well not exist as far as the fossil record is concerned. Jellyfish, worms, slugs, anything without hard parts. They decay completely within days or weeks. The exceptional fossil sites that do preserve soft tissue, places like the Burgess Shale or the Solnhofen limestone, these are so rare and so celebrated precisely because they're bizarre anomalies. The normal fossil record tells us almost nothing about soft-bodied life. This creates enormous blind spots in our understanding. So here we are, looking back across billions of years, seeing only the tiniest fraction of what actually happened. The fossil record gives us outlines and shadows, sketches where we desperately want detailed paintings, and yet from that impossibly sparse record, paleontologists have reconstructed the broad outlines of life's history on Earth. The rise and fall of dinosaurs, the age of mammals, the branching tree of human evolution. It's detective work with 99% of the evidence missing. The Pliocene, with all its crucial human evolutionary developments, mostly invisible. The Pleistocene ice ages with their shifting landscapes and megafauna extinctions poorly understood. The Pleistocene coasts, now underwater, completely inaccessible. The gaps aren't failures of science. They're features of deep time itself, reminders that most of Earth's story has been erased, that we're only ever seeing fragments, and that some questions might never have answers. We've walked through 66 million years of Earth's history. We've seen continents shift, climates transform, entire dynasties of life rise and fall. And you know what we've learned? We know almost nothing. Not because scientists haven't looked hard enough, but because the Earth itself seems determined to keep its secrets. Every discovery reveals new mysteries. Every fossil raises more questions than it answers. And maybe that's okay. Maybe the point isn't to solve the mystery completely, but to acknowledge that we're small, that history is vast, and that most of what happened in this world will remain forever hidden. So if you're still awake, or drifting in that pleasant space between consciousness and sleep, think about this. Right now, as you rest, somewhere in the world, a paleontologist is carefully brushing dust away from a bone exposed in a cliff face. Maybe it's a fragment that will rewrite everything we know. Maybe it's a piece of a puzzle we've been missing for decades. Maybe it's just another lost voice from an incomprehensibly distant past, trying to tell us something we'll never fully understand. The gaps remain, but they're not empty. They're full of mysteries of creatures that walked this planet and left no trace, of stories that happened in the darkness and will never be told. And somehow, despite all that absence, despite all that loss, we're here. We're the descendants of survivors, products of impossible odds, inheritors of a history so vast and so broken that we can barely see it. That's the real mystery. Not why the evidence is missing, but how we got here anyway. Sleep well. Dream of times before humans, of epochs lost to deep time, of the millions of years that made our world and then vanished. The gaps are waiting,